right, so in this next section, we're going to do the opposite. What if I give you the molar solubility, now you come up with the KSP? Well, that sounds like a plan. This is just like when if I gave you the pH, you solve for Ka. All right, we're doing the opposite. So let's see here. What do you think the very first thing you ought to do? Obviously, I left my double arrows behind. You need to write down your equation. And here is your ice table, all right? And what's the beautiful thing about this? This is a solid. And you notice we start, whoops, well, okay, they'll go here. Start off with your zeros, okay? There's my X, and here's my X. Now, what did they tell me? They told me that the molar solubility is that value, correct? So that's what X is actually equal to. X is equal to copper ion plus, and it's also equal to bromide ion, and it's 2.0 times 10 to the negative fourth, okay? So now we just start plugging numbers in. So the KSP is equal, there's my law of mass action, and they're both equal to X. Well, I know what X is. It's 2.0 times 10 to the negative fourth, so I have to square it. I don't think you need a calculator, do you? You get 4.0 times 10 to the negative eighth, okay? So that's a pretty easy one. That's where you know what X is, okay? Well, let's go ahead and do problem number 19. Okay, so the molar solubility of silver sulfate in pure water, all right, and here it is. It's there's your X, so calculate KSP. So I'm going to set up my ice table, all right? You could probably do this without me, all right? And my initial concentrations are 0. Now what? Be careful. This is a plus 2X, that's a plus X. And there you go. Now, what is it that they told me? They told me that X, not 2X, just X. Well, I defined X as sulfate, didn't I? And that's equal to 1.2 times 10 to the negative fifth. All right, so here is this. And I find it easier to go ahead and plug in the quantities here. So this is 2X squared times X, which is 4X cubed. And so I'm just going to plug in that value once. So here is my X cubed times 4, and I got KSP equals 6.9 times 10 to the negative 15th. You could, if you truly wanted to, do something like this. All right, so I'll just kind of start right here again. So here's my AG squared times X. And if you wanted to, you could have multiplied your 1.2 times 10 to the negative fifth times 2 at this point, and then square it. You're welcome to do that, times X, and guess what you get? You get the same answer again, 6.9 times 10 to the negative 15th. So either way, my personal likes is to go this route. Just combine all your terms, plug in X once, in this case, cube it, all right? Now, problem number 20 is a fun one. All right, why don't you pause this, work this whole thing out, but be really, really careful, all right? So, you know, pause this, do it, and come back when you're done. Okay, so calculate the KSP value for bismuth sulfide, which has a solubility of 1 times 10 to the negative 15th. That's your X again, isn't it? So that's your molar solubility. Well, what made this so interesting that you have a 2X and a 3X, okay? So when you put this in the law of mass action, you get 2X squared times 3X cubed. Well, what's 2 squared? That's 4X squared. What's 3 times 3? 9. Times 3, 27. So it's 27X cubed. And when you combine, you're like, whoops, that's not 54. What am I doing over here? Oh, I just fixed my boo-boo there. All right, so 4 times 27 is not 54, it's 108, X to the fifth. So here's my 108. Here's my X. X is my molar solubility, all right, that they gave me up here. So that is my X. So I took that to my fifth times 108, and you get 1.08 times 10 to the negative 73. If you want to talk about sig figs, then what should my answer be? 1.1 times 10 to the negative 73, because this has 2 sig figs. Wasn't that fun? I thought that was kind of fun. All right, let's see what's next. All right, so this topic is KSP and relative solubilities. In other words, what is the relationship between the KSP values and their molar solubilities, all right? Can I just look at the KSP value and say, oh, this one is going to dissolve more than this one? And the answer is, well, maybe. That's a great answer, maybe, all right? Now, If the salts being compared produce different number of ions in solution, then you can't compare their solubilities. For example, how many ions do we get here? We get 3 ions. How many do we get here? 2 ions. So I can't say, well, the KSP for magnesium hydroxide is smaller than the KSP for copper 1 bromide. Therefore, you have a smaller solubility. That doesn't work because here you're going to have a cube root and here you're going to have a square root. So you can't compare them directly by looking at their KSPs. However, all right, if your salts being compared produce the same number of ions in solution, then you can compare them directly. All right, so for example, if you want to compare sodium chloride and potassium fluoride, the KSPs both are going to be equal to x squared. So if you take their square roots, you're going to still have the same order than you would their KSPs, okay? So the molar solubility will be directly related to the order of the KSPs. So in problem number 21, compare the solubilities of those 3. So in other words, find the, which one will dissolve better, okay? And pause this and try to work it out yourself. All right, hopefully you came up with something good. All right, and this is what I came up with. Because they're both 2 ions, silver ion iodide, copper ion iodide ion, copper iodide or copper ion and sulfate ion. They both have only 2 ions being produced. So the one that has the biggest KSP value will have the greatest solubility. The more of it will dissolve in solution. So copper sulfate has 10 to the negative 5th, so that solubility is greater than 10 to the negative 10th. So that's silver iodide, which is greater than 10 to the negative 12. So this one, copper 1 iodide, will dissolve the least out of those 3 in solution, okay? Now, what about problem number 22? It says compare the solubilities of these 3. Now, what did you notice about those 3? They all give you different amounts of ions. Here you're going to have 2 ions, here you have 3 ions, and here you have 5 ions, all right? So what are you going to do? Well, figure out their x's, okay, and then go from there. All right, so I solved for x. So in the case of a copper 2 sulfide, I just basically took the square root because I made 2 ions, so I'll take the square root. And I got 9.2 times 10 to the negative 23. For silver sulfide, this is equal to 4x cubed. So first I divided by 4, and then I took the cube root, and it's 3.4 times 10 to the negative 10th. And then here, well, we just did a problem like that, but if you needed to go backwards, I first divided by 108, and then I took the 5th root of that. So I got 1.0 times 10 to the negative 15th. If you look on the prior page, that is the molar solubility that we started with. So if I wanted to, I should put the units, molarity, behind each one of these numbers, shouldn't I? All right, and then that would make sense. So now we can compare. So which one will dissolve the best? Well, this one has the highest value. 10 to the negative 15th is bigger than 10 to the negative 17th, which is bigger than 10 to the negative, 23. So this is the ranking order. So even though the KSP for bismuth 3 sulfide is by far the most negative, 10 to the negative 73, it actually dissolves the best because you had to take a 5th root of that, okay? So this next section, oh boy, all right, I put a star by this, all right? This is a very common problem on the AP exam, all right? It's called the common ion effect, okay? So the solubility of a solid is what? Lowered. Ooh, think about that. If a solution already contains ions common to that solid, and that's called the common ion effect, all right? So the example is, what if calcium fluoride were going to be placed in a solution of sodium fluoride, all right? So what is my common ion? Fluoride. That means I'm going to have more fluoride ions. It increases, so it's going to shift to the left. So if it's going to shift to the left, what's going to happen to our x value? Both of these values are going to go down, aren't they? So the solubility goes down, and you're going to make more solid, okay? And that may ring a bell because that's a Le Chatelier shift, all right? So if more F negative is added, it's going to shift to the left. The molar solubilities are going to decrease, all right? So, oh, silly Mrs. Vandewy, that's what's down here, meaning I need to put in the word shift left, don't I? Here, let me type this in. L-E-F-T. There we go. Now that makes more sense. There we go. It's going to shift left, meaning the molar solubilities will decrease, okay? So in general, the solubility of an ionic compound is lower in a solution containing the common ion than in pure water. So example B says calculate the solubility of calcium fluoride in pure water, then calculate it in a 0.1 molar of sodium fluoride, all right? So watch what I do here. So this is just like the ones that we've done already. This is important. If you just put it in pure water, your initial concentrations are both 0. And this is setting up just like what we have done before, okay? So the KSP is this. Well, the KSP is equal to x times 2x squared, which equals 4x cubed. Well, x equals 2.1 times 10 to the negative fourth. Oops, you know what? I left out a step here, and there we go. All right, so here's your molar solubility, okay? Now watch what happens if you put it in a solution of sodium fluoride. All right, so here is, oh, look at that. I have initial concentration. I already have some fluoride. Where'd that come from? It came from right here. Notice when this jumps in the water, I have a 0.1 molar solution of sodium ion, and I have a 0.1 molar solution of fluoride ion, all right? Only because there is no subscript to fluoride. Think about that for future, okay? So here is this. So now this is x plus 2x, and look what I have here. So my KSP is this, and here is with my 0.100 plus 2x. Well, take a wild step. What do you think I can do here? All right, I'm going to assume the x is small. All right, so what happens here? Well, my KSP is still 4.0 times 10 to the negative 11th. Equals, well, where did this 0.01 come from? That's 0.1 squared times x, all right? So x is equal to 4.0 times 10 to the negative 9th. So look at the molar solubility. This is the amount of ion in solution, and the calcium ion in solution, that's your x, all right? Without fluoride already being there. This is the molar solubility, let's say, of calcium, because that's just an x, with the fluoride in there. So what's my conclusion? All right, without the common ion, the molar solubility was 2.1 times 10 to the negative 4. With the common ion, the molar solubility is 4.0 times 10 to the negative 9. So what just happened? The molar solubility decreased with the common ion. All right, go back and look at this problem again if you need to digest what I just said. All right. This is in total compliance with Le Chatelier, all right? So we mathematically proved Le Chatelier saying it's going to shift to the left, so x is going to go down, okay? Let's go to the next page. All right, so calculate the molar solubility of calcium fluoride in solution now contain the common ion calcium. So take a wild step, even before you do any math. What do you think is going to happen to your x value? Is it going to be bigger or less than the 2.1 times 10 to the negative 4? Think about that, and let's see if your answer makes any sense, okay? So let's go ahead and do this. Here is my KSP. What can I do here? Well, in the same case as before, what can I assume? I can assume this is negligible, all right? X is small approximation. So now this equals 0.250 times 4x squared. Where did the 4 come from? 2 squared, right? And well, what's 0.25 times 4? That's just 1. So KSP now is equal to x squared. X squared is equal to 1.46 times 10 to the negative 10th. And x equals 1.2 times 10 to the 5th. And so that is our molar solubility. So what just happened? All right, did it go down? Yeah, last time it was at 1.2 times 10 to the negative 4. Now it, or 2 point whatever, it was to the negative 4 before. Now it's the negative 5th. Molar solubility still went down. Now I think I need to quit here. It's almost time. So I think we need a part 3. So don't wait to be great, and we'll see you shortly. Bye-bye.